Our lesson for today will be looking at chemistry 1502. The topic for today is elimination reaction. E2 lesson 103. Let us start. It is very important to watch the first lesson videos based on elimination, that is lesson 101 and lesson 102, so that you can know the difference between E1 and E2. Now in this lesson we'll be looking at E2, which is also called biomolecular elimination. It's an elimination that can also take place under second order conditions with a strong base present. As you can see the difference now between E1 and E2. E1, it only requires a weak base. E2, it requires a strong base. And E1, we only have one reaction taking place, or one transition taking place, whereby we have the rate limiting step, and then the second transition is where we have the base deprotonating the hydrogen adjacent, the hydrogen from the carbon adjacent to the carbocation. Now looking at the biomolecular elimination, it simply means that we have two reactions taking place at the same time, whereby the leaving group leaves the substrate, the base deprotonating the hydrogen at the same time. We only have one transition. So that is why we say it's a biomolecular. Bi means two reactions taking place in under one transition. And another difference, I repeat, is that this requires a strong base. Remember that in elimination we don't talk about nucleophiles. As usual, we are going to start with the general equation. Suppose we have the substrate undergoing E2 reaction. Remember that we said this is a biomolecular elimination. So we are going to have our substrate, our leaving group leaving the substrate, at the same time a strong base deprotonating. At the same time, the bond, the pi bond formation occurring. Then we can quickly look at the transition state, whereby we have the formation of a new bond here with the existing bond, and we know that hydrogen will be deprotonated. There will be a bond between our base and the hydrogen, which will bear a partial negative charge, and then we have those existing bonds, and then we have the leaving group leaving, which will also have a partial negative charge. And then the product will be an alkyl. With the leaving group being an ion, and we can write the new bond of a base and that hydrogen. So you can see the difference. Everything is happening in one transition. That is why we say it's bimolecule. Living group leaves the base, and it has to be a strong base, deprotonates at the same time. So that is general equation of E2. For the first example to demonstrate E2, let us use one of the examples that we have in one of the textbooks. So it's a reaction between bromopentane with sodium ethoxide. So sodium ethoxide looking at this, you might say it is not a strong base, but once we separate the ions, we have sodium, positive charge, and we are going to have oxygen as a negatively charged. This will result into be a strong base. So what happens is that, remember, it is E2, the living group will leave, the strong base will deprotonate. At the same time, you're going to have, and the reason why I chose this carbon, you can see that this carbon, it is a secondary carbon, it is bonded to two other carbons, and also this one, it is a secondary carbon, so it doesn't really matter. Then our product will have a double bond, it is pentene, and you can see this is a trans pentene. Remember that between cis and trans tend to be the most stable. So the major product is trans pentene. So you can see the difference between E1 and E2. Now looking at conditions of E2, one of the important things is to know that it requires a strong base. And the reactivity is not the same as SN2, but it is the same as the SN1 and the E1. And those strong bases can also be part of the strong nucleophiles from SN2. And with the E2, we have to apply the Zanzev rule. But we also have another rule, which is Hoffman. Let us quickly look at this reaction. We are reacting it with a strong base, which is hydroxide. This reaction will undergo E2, so it means we have a living group leaving, and then we have two options. Remember that question might say major minor product. So how do we produce the minor and the major product? So suppose the base deprotonates this hydrogen, or the base deprotonates this hydrogen. So the pink one, I'm going to use this color to represent the deprotonation of this hydrogen here. And then the green one, I will use it I'll use this color for the structure. So let us start with the green one. The green one, we are going to have this forming a bond here. So let us quickly draw this. So it's carbon. On this carbon we have a double bond. So we did not do anything with this one. And then this one only has one hydrogen. Then this one we did not tamper with anything, it has two. Now we look at the substitution. We have 1, 2, so it is di-substituted. There's actually something wrong here. Remember that the carbon which had the leaving group, it's actually carbon number 2. So what must happen is that the carbocation, it's actually here, even though we don't have that step, we don't have the rate limiting step. Let me just do this. This is the carbon that we need the double bond. So instead of having the double bond here, our double bond will be here, because we deprotonated carbon number 3. So carbon number 3 is this one. So we can put hydrogen here, and this one it only needs 1. So looking at the substitution, we have 1, 2, it is di-substituted. And then with the product of the pink color, we are going to have, we have 1, 2, 3, 4. So we deprotonate this, and then we are going to have a double bond here. So the double bond is actually here. Then we can just put, it's only 1. Then we have 1 here, we have 2 here, we have 3 here. So in this case you can see that this one, it is less substituted. These are the carbons in the double bond, and other carbons which are bonded to this double bond carbons, it's only 1. So in this case we say this is the major because it is more substituted, sense of rule. This is the minor. E2 has more parts, or let me say has more conditions compared to E1. Now we do have different types of bases, and we do have big bases, and they are very important when it comes to E2. Sometimes instead of big bases we use the word bulky bases. Now why do we use bulky bases? We normally use bulky bases to produce a Hofmann product instead of a Zainzeff product. One of the most common bulky base used to produce a Hofmann is tert butoxide. There are many of them, like diisopropylamine, triethylamine. We also have the 2,6 dimethylpyridine, but the most common one is tert butoxide. And the formula, or the structural formula, it's like this. You can see it is bulky, not long but bulky, big. So these types of bulky bases, we use them to produce a Hofmann product. Now demonstration, or looking at this using a reaction, can be more understanding compared to looking at the theory part. I normally want to use the examples that you can be able to access with most of the common chemistry, organic chemistry textbooks. So let us look at this. It's also accessible to understand this better. Let us actually use not a condensed structure. Let us use this as our first example, or to explain the bulky base. We use ethoxide as our base, in methanol. So ethoxide will have in methanol. So in this case, you can see that this is not a bulky base. And remember, we are dealing with E2 reaction. So this is not a bulky base. It can easily deprotonate any hydrogen. It can easily leave out all the hydrogens and go to the one which will give out the most substituted product, which is this one. Since it is not bulk, it is not big, so it can navigate and go to the hydrogen of its choice, so that it can produce the most substituted product. And this will actually give out the major product according to Zainzev, which is the most substituted, as this leaves, and then the double bond will be formed here. Then our product will be this one. And you should know that this base, as it deprotonates this hydrogen, these parts of this organic structure, organic molecule, can try to stop the base. But in this case, the base, it is not big, so it can actually maneuver and go to the hydrogen of its choice, so that it can produce a stable or a major product. Now let us look at when we have a bulky base. Let us use the very same structure, but this time we are going to use a bulky base. Remember that when we have something like this, it simply means our base, it's actually our base, it's like this, is the T-ted butoxide. So you can see this is a big base compared to the one that we had here. So in this case, it will be very difficult for this big base to maneuver and go to the hydrogen of its choice. So what happens is that it will just go for the hydrogen which is close to it. So the target hydrogen can be these ones which are very close to it. So as the leaving group leaves, the bulky base will decide to just deprotonate any hydrogen which is very close, and then we are going to have our bond here. So drawing the product, we have 4 of them, and then we are going to have a double bond here, and then we are going to have our hydrogens here. Let us actually use the cis and trans. Then we are going to have CH2 here and CH3. It's actually this part, and then here we have it will be CH3. Don't be confused, this CH3 is this one, and then the CH2 CH3 is this one. Then this is the carbon that we are looking at. So in this case, this will be the major product, even though it is not more substituted compared to when we deprotonate this hydrogen. But since we have a bulky base, so this is one of the conditions. If you have a bulky base, just know that the Hofmann product will be the major. So one of the conditions that you have to add, if we have a bulky base or a big base, Hofmann product will be the major. In the next lesson video, we'll be looking at more examples on how to determine whether it will respect the Zainzev or the Hofmann product. That's it for this lesson video. This is Wahula SJ. Thank you very much.